Good morning, good afternoon, good evening. Welcome to today's session on automatically managing partitioned data on Amazon RDS for Postgres. My name is Wada He. I'm a principal database specialist, solution architect with Amazon Web Services. In this session, I will give a brief introduction of Amazon RDS for Postgres, talk about table partitioning, what is partitioning, why there is a need to partition, and we will walk through an example of using partitioning to automatically manage time series data. At the end of the session, I will summarize with partitioning best practices. Let's go right into it. For those who are new to Postgres, Postgres is an open source object relational database, emphasized on extendability and SQL compliance. It was originally developed as the Postgres project back in 1986 in UC Berkeley. It has been in active development for more than 30 years now. It has earned a strong reputation for its proven architecture, reliability, rich feature sets, and extendability. It's well known for its strong development community behind the software. The community developed and maintained a rich set of extensions that adds on the core Postgres functionality. Managing day-to-day operations and running a highly available database are complex and time-consuming. You need to manage failover in case of a software or hardware failure, perform backup recovery of database, keep the OS and database version up to date, and manage security and compliance. Also, you need to take care of monitoring and maintaining the performance level of the database. Amazon Managed Database simplifies the deployment and management of running a database. It takes care of day-to-day tasks for managing the database, leaving you with tasks that matters most to your application. For example, schema design, query construction, and query optimization. Amazon Relational Database Services, or Amazon RDS, including Amazon Aurora, is our collection of managed database services that makes it simple to set up, operate, and scale databases in the cloud in just a few clicks. Launched in 2009, customers benefit from over a decade of proven operational expertise, security best practices, and innovations for cloud-native databases. As a managed database, Amazon RDS helps to remove inefficient and time-consuming database administrative tasks without needing to provision infrastructure or maintain software. As a result of this innovation, Amazon RDS offers you the ability to customize your managed workload for the high availability and durability you need. Also, it provides the freedom and broadest choice to deploy and scale the relational database of your choice in the cloud or on premises. With Amazon RDS, customers have the choice to deploy on any of the 7 managed database engines in the cloud, including Amazon Aurora for MySQL compatibility, Amazon Aurora for Postgres compatibility, Amazon RDS for MariaDB, Amazon RDS for MySQL, Amazon RDS for Postgres, Amazon RDS for Oracle, and Amazon RDS for SQL Server. Our session today will be focusing on Amazon RDS for Postgres, specifically looking into Amazon RDS for Postgres partitioning features for managing time series data. What is Postgres partitioning? Why do we need it? Back in 20, 30 years ago, we were measuring data in gigabytes. Now we're talking about terabytes and petabytes of data, especially in the recent years. With the stay-at-home order, there is a sudden spike of demands for online services business. For example, the online shopping and delivery apps and the online gaming industry all of a sudden becomes hugely popular. Along with the sudden growth of business, the databases backing those applications also experienced a rapid growth. Size of table becomes so large that its working set can no longer fit in memory. Database on this footprint is approaching infrastructure limits. Query response time increased beyond SLA, and routine maintenance operations are taking much longer. And those are all the challenges that are associated with those rapid growth of business. We need a way to manage the growth. Postgres table partitioning allows us to divide a large table into multiple segments called partitions. Once a table is partitioned, operations such as backup, restore, index maintenance, vacuum, and query execution can be performed at the partition level. We can implement data retention with easy adding and removing partitions. Postgres table partitioning significantly reduces the amount of data to touch for query executions and for routine operations, provides an effective solution for maintaining operational and performance SLAs under rapid growth. Let's take a closer look at Postgres table partitioning feature. Before Postgres 10, Postgres users partitioned their data using inheritance-based partitioning. The method uses constraints to define the partitions and rules or triggers to route the data to appropriate partitions. A user had to write and maintain codes for that. Postgres 10 introduced declarative partitioning, which is much easier to set up and maintain. Each Postgres version continues to add functionalities and performance enhancements to partitioning. Postgres 11 offers most of the partitioning-based features. Postgres 12 added enhancements for query pruning and support for foreign keys, and also reduced locking on attached table. Postgres version 13 added logical replication support. Version 14 added concurrent detached partition support and also improved the update and delete performance for large number of partitions. With Postgres declarative partitioning, partitioned table itself is a virtual table, having no storage of its own. Instead, the storage belongs to the partition. Partitions themselves are also tables associated with the partition table. Each partition stores a subset of data as defined by its partition bounds. All rows inserted into the partitioned table will be routed to the appropriate one of the partitions based on the value of the partition key columns and the partition bounds. Updating the partition key of a row you cause it to move into a different partition if it no longer satisfies the partition bound of its original partition. You can define a default partition. A default partition stores data that does not belong to any partitions. You can also create multi-level partitioning with subpartitions. A subpartition means a partition may also be a partitioned table itself. To start with partitioning, you need to decide on the partition strategy. First thing to decide on is how you want to divide the data by choosing a partitioning type. In general, you want to divide the data to serve at least one of the two objectives. First is to enhance query execution. That is, target query executions to a subset of partitions. The second objective is to enable data lifecycle management. You want to be able to add a partition or remove a partition with minimum impacts to your online workloads. Postgres supports partitioning by range, by list, or by a hash function. With range partitioning, data is placed in partitions according to a range of values. For example, separating data by sales date, emission date, and etc. Range partitioning can be effective when you want to access time series data by specifying date such as year or month. With list partitioning, data is partitioned according to the specified values. For example, separating data by region, department, and etc. List partitioning can be effective when your query needs to group data by a specific value. For example, regions. Started with version 11, Postgres also supports hash partitioning. Hash partitioning allows you to distribute data across partitions based on hash algorithm applied to a key. Hash partitioning is effective when you want to break down a large table and distribute data evenly across partitions. After deciding on the partitioning type, you also need to choose which column or columns to use as partition key. A range or hash partition key can make up of a column or a set of columns, or an immutable expression. A list partition key must be a single column or expression. Knowing your data and query access pattern is important for deciding on the partition key. For example, as we talked about before, if you need to access the data by time range, then a timestamp column would be a good candidate for partition key. If you frequently request data that needs to group by a specific value, such as department, then the department column would be a good candidate for partition key. Selecting the right partition key is critical in order to meet the objectives for partitioning. Take a look at the where course of your queries. The partitioning key column or columns should be included in the search condition of the query. After deciding on the partitioning strategy, you also need to define the lower bound and upper bound values for the partitions. A partition bound behaves like a check constraint. Whenever data is inserted or retrieved, it determines which partition to perform the operation on. The partition lower bound is inclusive. The upper bound is exclusive. You don't need to worry about defining bounds to balance data across partitions. It's perfectly fine to have a partition that have more rows and another partition with less rows. Partition bounds cannot have overlaps. You will receive error if there is an overlap. We have talked about the challenges of rapid business growth, why partitioning is a good fit for managing data growth, and how to start with partitioning. Now let's take a look at an example of using partitioning to automate the management of time series data. Before we get into the example, first, what is time series data? From a database perspective, time series data have a few key characteristics. Time series data is typically inserted but not updated. As time series data changes, new entries are added to the table. The original rows are treated as immutable. The new information is appended to the table. Old rows may be deleted if purging is needed, but they are not changed. The data behave more like an append log. Access to time series data is not as random as is typically seen in an OLTP database. Many organizations need to store time series data. Some organizations have data streaming from a fleet of Internet of Things devices. Others may have single table of time series data, such as a transaction history table in an OLTP database. When it comes to choices of database for storing time series data, both relational databases like Amazon RDS for Postgres or a purpose-built database like Amazon TimeStream are popular choices of databases. For example, if you already have data in Postgres database and you need to run queries between the existing relational data and time series data, or if you frequently do load of data in large groups of batches, then RDS Postgres is a good choice for storing those time series data. If the time series data is to be used in a standalone application, or if the data will be loaded directly from many locations or sensors in a streaming fashion, then a purpose-built database like Amazon TimeStream will be a good choice for storing those time stream data. Our example today will focus on using Amazon RDS for Postgres to manage time series data. Our example here is an online delivery app. With the stay-at-home order in the recent years, our online delivery app has experienced a sudden, unexpected boom of business. From a database perspective, we have a transaction history table that keeps track of all transaction activities. Transaction activities are inserted only, but never updated. Because of the nature of the data, the size of the table is growing at a rapid rate. And that's becoming very difficult to manage. The size of the table is now at 10 terabytes, and we are seeing a 2 terabyte per week growth rate. Operations such as vacuum is taking weeks to finish. Querying against the table takes a long time. We are also seeing locking and blocking issues on the table. Our customer never cares for information older than 90 days, and there are a lot of historical data in the table that can be archived. Looking at the schema for the transaction history table, there is a time column that records the time of the activity, which is of a timestamp data type. A transaction ID column, a total column that stores the amount of the transaction, and a status column. And there's also a transaction detail column that's a JSON column, and it stores the detail of the transaction. Now we are looking for an effective way to manage the size of the table, reduce query response time. We also want to start implementing data lifecycle management. We need the most recent 90 days of data in the table only. We would like to archive older data. We have been trying to delete some of the historical data off the table, but that caused a huge bloat issue for us. This transaction history table looks like a classic example of time series data. From what we learned about table partitioning, range partitioning is a good solution for managing time series data in this type of use cases. Data is frequently accessed by date range. Table schema has a time column that can be used as partition key. Data older than 90 days can be archived. Means we only need to keep 90 days of data in the partitioned table. If we partition by day, we will end up with about 90 partitions. That should be a manageable size. We can implement range partitioning for this table. With declarative partitioning, creating the partitioned parent table is similar to the regular create table. We just need to add a partition by clause to the create table statement. Once the partitioned parent table is created, we need to create a table for the partitions. With native Postgres, there is no support for automatic creation of partition child tables. We need to call create table 90 times to create each partition. We also need to manually create new partitions and remove age partitions to have the most recent days of data in the partition table. We can script that and schedule a job to help with the ongoing maintenance. This manual process certainly works. However, it can be cumbersome. Starting with Postgres version 12.15, Amazon RDS for Postgres supports pgpodman and pgcon extensions. And that makes partitioning management much easier. pgpodman is an extension that can be used for easier setup of tables and automatic management of the partitions. pgcon is an extension that allows us to use the con syntax to schedule Postgres commands directly within the database. We can further enhance our partitioning solution by automating the creation and management of table partitioning using pgcon and pgpodman. pgpodman automates the operations for creating a partition parent table, continuously creation of partition child tables and attach them to the partition parent table. And it also takes care of data lifecycle management for us with the ability to detach and drop age partitions. To enable pgpartment on RDS for Postgres, we need to run create schema for partment and then create pgpartment extension for each of the database we would like to enable pgpartment. Instead of manually creating the partition parent table, calling create table 90 times to create each partition child table, pgpartment can automate the create parent table and partition child tables and take care of the ongoing partitions management with a single create parent call. Here we are calling the partment create parent function. We're telling partment to create a transaction history partition table in the public schema, using time column as the partition key. And we are specifying the partition type as Postgres native partitioning. The time interval is daily. And we are also asking pgpartment to create the first partition starting 90 days ago. pgpartment by default creates 4 partitions ahead of time. Here, with the create parent call, we are looking at about 94 partitions with the initial partitioning setup. pgpartment will take care of the ongoing creation of new child partitions continuously. The cool thing about create parent is that it's a one-time call of the function. Once we define the partitioning policy, pgpartment will take care of automatically maintaining partitioning ongoing, adding new partitions as needed, as well as remove age partitions based on the policy defined. Since we are not interested in data that's older than 90 days, we can set data retention policies in pgpartment. We can call config function to set data retention for 90 days. For partition older than 90 days, we have a choice to detach the partition, keep it as a standalone table for later process, for example, archive to X3. Or if we don't need the data anymore, we can also set the retention keep table parameter to false to simply drop the partition. This maintenance operation is triggered whenever one maintenance proc function is called. Earlier on, we introduced pgcon. pgcon is a scheduler that allows us to use con syntax to schedule Postgres commands to run. If we would like to have partition maintenance to run at a certain time, for example, during off-grid hours, we can use pgcon to schedule partition maintenance. To enable pgcon on Amazon RDS for Postgres, we need to add pgcon to the share preload libraries parameter in the DB instance parameters group, and then create a pgcon extension. Now that we have implemented table partitioning on the transaction history table, let's take a look at what has improved. Most of our customer queries perform search based on time ranges. As a result of partitioning, we're seeing the effect of query pruning. Postgres Planner is able to limit index scans to a subset of related partitions instead of scanning the entire table. We are seeing partition-wise joins. The dataset the query has to touch in order to return results is much smaller. And we are seeing more efficient cache usage. Our query response time has significantly reduced and is looking well under SLA. Our bulk operations for batch insert and deletes are running much faster, also with minimum impacts to the online workloads. We can now do batch inserts into a partition, create indexes and constraints without impacting the online workload, and then attach the partition to the parent table with minimum logging. Similarly, bulk delete operations can be done at partition level by just detaching a partition concurrently, without worrying about vacuum cleanup or increased table bulk. With the transaction activity data continuously being added to the transaction history table, we have been looking for an effective way to help with archival of historical data. Partitioning and pgpartment helps to automate the data lifecycle management. It automatically detaches partitions older than 90 days and keeps the partition as a standalone table so that our archival process can come along later to move those data to S3 without impacting the online workloads. Now, time to look at the effectiveness of the range partitioning solution with the requirement of managing size of the table. Range partitioning divided data into 90 partitions. Each partition is about 3 gigabytes. pgpartment data retention policy automatically manages data retention to keep data for the most 90 days in the partition table. That effectively helps us to control the size of the table. With proper construction of query to include time range in the search conditions, we are able to get effective query pruning to reduce the amount of data a query needs to process in order to return results. Many of the routine operations such as index maintenance, vacuum, backup, restore can be performed at partition level. The overall query, as well as system performance, are improved because of that. pgpartment policy-based data retention automatically detaches partition older than 90 days without us worrying about the table bulk or vacuum cleanup. Our archival process can easily move historical data to S3 without impacting the online workloads. Range partitioning has been effective in meeting all the requirements for managing time series data in our transaction history table. So far, we have talked about the benefits of partitioning. However, partitioning is not for every use cases. When to use partitioning and what partitioning is not, let's take a look at best practices. When to consider partitioning. Partitioning is good for managing very large tables. Some criteria to consider. If you have tables that are larger than 100 million rows, or that the size of table has become so large that its working set is no longer able to fit in memory. If you have time-based or series-based data with continuously streaming of data in a pen-only fashion, historical data can be archived or discarded. Those type of tables tend to benefit from partitioning. If your application typically accesses data in the table by time range or by a specific value, or if you have tables that frequently receive data in large batches, those tables could be good candidates for partitioning. With all the benefits we share about partitioning, some people may say that let's just implement partitioning for every table. Partitioning is not a magic bullet. It's definitely not for every table. There are overheads on query planning as well as query execution for partitioning. When the dataset is too small, the cost will outweigh the benefit, not to mention the additional operational overhead and complexity associated with partitioning. Partitioning is also no substitute for good schema design. You will still need to follow your operational best practices. Partitioning is also no replacement for query tuning. You will still need to do your index tuning. Partitioning is not sharding. Partitioning is not about distributing data across multiple compute nodes. When implementing partitioning, a few best practices to note about. Before deciding on the partition key, take a look at your top queries. Know about the access pattern. What data does your query search for? What column or columns are most frequently appear in the where clause of the search condition? If you were to implement archival, which column or columns would you use to determine the data is aged? When considering candidates for partition key, you may also want to consider if the candidate will ever get updated. In general, you don't want to move rows from one partition to another because of the partition key gets changed. When deciding on partitioning strategy, the number of partitions you end up with can affect the performance of partitioning. Having too few partitions, you may end up with big partitions. You're not getting the benefit of partitioning. Having too many partitions, the overhead for query planning may be too high. Your query response time may increase. You need to find a balance point between manageability and query response time. You may also consider using multi-level partitioning to divide data into multiple levels to help with the balancing if you have extremely large data set. Some of the general best practices to consider. You want to start partitioning early before the table becomes too big and unmanageable. As we talked about earlier, Postgres make performance functionality enhancements to the partitioning feature in each version release. So you always want to upgrade to the latest major and minor version to take advantage of the latest enhancements. pgpartment and pgcon extensions adds capability on top of core Postgres to simplify partition management. You can use those extensions to automate partition management. With the current Postgres support for partitioning, there are still a few limitations that you should be aware of. When defining a primary key for a partitioned table, the partition key must be included as part of the primary key. Currently, there is no support for defining unique indexes across partitions. Uniqueness is supported at partition level only. If an update moves a row from one partition to another, there is a chance there is another concurrent update or delete operation will end up with serialization failure error. So it's best to choose columns that does not change for partition key. In summary, partitioning offers many benefits for managing very large tables such as time series table. The benefits could include enhanced query performance, the ability to target query execution to a subset of partitions, faster both insert and delete operations with minimum logging, and also data lifecycle management to manage the growth of the data. Knowing your data access pattern helps to create an effective partitioning strategy. Partitioning is a database-level technology that enhances management of large data sets. It's completely transparent to the application. It does not require any application code change to adopt the technology. You should be aware that partitioning is not a solution for every table. It has additional performance and operational overheads. You should carefully evaluate before implementing partitioning. This concludes our session on automatically managing partitioned data on Amazon RDS for Postgres. Thanks for attending.